Hello everyone, and welcome back to my YouTube channel. My name is Nathan Rodriguez, and today we will be expanding on our previous topic of neural networks, and we will be talking about gradient descent today. So the main material that we used this week was the Gradient Descent, How Neural Networks Learn YouTube video by 3 Blue 1 Brown, and then a Nobel Prize lecture by Demis Hassabis, who is an AI researcher and CEO and co-founder of Google's DeepMind. So neural networks are a fundamental concept in artificial intelligence and machine learning where they learn through the minimization of a cost function. Now, this cost function quantifies the difference between the network's predicted outputs and the actual desired outputs. The main goal of training a neural network is to adjust its internal parameters, namely weights and biases, such that a difference is minimized. By doing so, the network increases its ability to make correct predictions or classifications regarding incoming data. Now, gradient descent is the most implemented optimization algorithm for neural networks when it comes to minimizing the cost function. Gradient descent is the most implemented optimization algorithm for neural networks when it comes to minimizing the cost function. It is a way to iteratively find the minimum of the cost function, and it follows the direction of the steepest descent. This is achieved by computing the gradient of the cost function, a mathematical representation of its slope, and doing an update with respect to weights and biases with small steps. Most importantly, it gives a gradient vector that provides valuable information how each parameter contributes to the overall error, with larger magnitudes indicating a greater impact on the network's performance. The general idea of gradient descent is that it is always making small steps in a particular direction so that it can gradually reduce errors and start making good predictions. A very important technique that makes the computation of gradients effective is backpropagation. Now, backpropagation is a procedure that systematically computes the gradient of the cost function with respect to each weight and bias in the network. It uses the chain rule of calculus to backpropagate the errors from the output layer towards the early layers, enabling the network to easily compute how a given update should be made for each parameter. Without backpropagation, the process of training would be considerably slower and computationally impractical for deep networks with many layers. The most critical elements of a neural network are, in fact, its parameters, weights and biases, that literally define its behavior and ability to learn. Weights dictate the strength of connections between neurons, essentially controlling how information flows to the network. In contrast, the bias serves as an offset to help neurons fire up even when input values are low. Now, this allows greater flexibility for the network to capture patterns and data. These parameters are continuously fine-tuned during the training process in an effort to improve network performance. To accomplish this, one must make the neural network see a large dataset of labeled examples in order to learn patterns from the data. It starts modifying its parameters based on the feedback that it gets from the cost function and gradually enhances its ability to recognize a relation between input and output. After training, the network's ability to generalize is checked by testing its performance on new, previously unseen data. If it performs well on this unseen data, that means this network learned general patterns rather than just memorizing the training examples. For gradient descent to work well, the cost function should be smooth and differentiable. The smoothness of the cost function means that with small variations of weights and biases, the function's output has small, well-specified changes, allowing the optimization algorithm to easily converge to a local minimum. But if the cost function were very irregular or contained sharp jumps in it, the gradient descent would hardly converge to any optimal solution. Now, these are general principles in neural networks and optimization and are included on advanced AI systems such as AlphaFold. Now, AlphaFold is an artificial intelligence system applying similar machine learning methodologies to predict three-dimensional structures of proteins at high resolution. It was trained on a massive dataset of experimentally determined protein structures, enabling it to learn the underlying patterns and physical constraints that govern protein folding. Again, it is the self-learning process through which AlphaFold keeps building up its own predictions and designs new strategies towards higher accuracy. Altogether, AlphaFold 2 came to a major development from its version by embedding an evolutionary information model with physical constraints and a deep learning way for atomic accuracy of protein structures, a sensational break in biological research. The AlphaFold database has given researchers access to a wide repository of predicted protein structures that accelerate drug discovery, disease research, and biotechnology. The latest version, AlphaFold 3, further extends its capabilities by modeling interactions between proteins and other molecules, making it even more powerful for studying biochemical systems. Beyond AlphaFold, AI-driven systems have shown remarkable success in solving complex problems in large combinatorial search spaces. One such prime example is AlphaGo, which mastered Go by learning from data a model provided that guided the search for the best moves. These AI models provided an objective and iteratively refined a strategy from which to find the best possible solution. This ability to explore vast solution spaces efficiently renders AI indispensable, from scientific discovery down to strategic decision-making. The success of AlphaFold really shows the magic of gradient descent as a basic optimization technique. Deep neural networks need to be trained on complex spatial and biochemical patterns from vast data in order to predict protein structure. That is to say, gradient descent allows this training by iteratively refining the network's parameters towards better performance at each step in the training model. No efficient optimization methods like gradient descent exist. And without it, deep networks cannot be trained on big datasets, allowing for breakthroughs in AI which simply could not happen, such as AlphaFold. Beyond biology, many AI-driven scientific discoveries are made possible by gradient descent. In chemistry and material sciences, gradient descent is employed to train deep learning models in the prediction of molecular interactions, fast-forwarding chemical reactions of interest. Convergence on some properties through minimizing cost functions accounting for differences in predicted actual outcomes quickly deliver promising compounds or materials. This greatly cuts down the time and resources needed for experimental testing, accelerating processes in drug discovery, renewable energy, and nanotechnology. Another key aspect with gradient descent is the cost function must be well-behaved and differentiable. A cost function having sharp discontinuities can render an optimization process incapable of making any reasonable improvement. This explains why smooth kinds of activation functions like the ReLU and sigmoid have become popular in deep learning models. Both functions remain differentiable while still letting networks learn sophisticated relationships within the data. This allows applications such as AlphaFold to iteratively refine the model's prediction of protein structure, with each step of optimization yielding more accurate and biologically meaningful results. The further improvements in optimization techniques, such as more efficient variants of gradient descent, will probably underlie the future of AI-driven discovery. This will remain the fuel to study better convergence speed, low computational costs, and stability of training as the models grow large and datasets more complex. Among the most promising directions is including methods of gradient-free optimization reinforcement learning and evolutionary algorithms complementary to gradient descent in settings where it is hard or expensive to compute or differentiate cost functions. In all, gradient descent is a fundamental building block of modern AI that allows neural networks to learn, adapt, and realize breakthroughs from protein folding to strategic decision-making. This optimization technique has powered some of the most mind-blowing advances in machine learning by iteratively updating model parameters toward minimum error. And as long as AI technology continues to evolve, so will innovations around gradient-based optimization be necessary for extending frontiers in scientific discovery and real-world applications.